Welcome to the Explainer. So glad you're here because today we're diving into something that, honestly, gets a pretty bad rap. A lot of people mistakenly think our topic today is just about memorizing dry, dusty rules, but that really couldn't be further from the truth. Today, we're unpacking number theory, and we're going to explore it not as a boring list of formulas, but as the universal language of patterns that literally governs everything around us. Think about it for a second. It's a pretty deep question. Is math just a bunch of random, frustrating rules you have to memorize for a test? Or is it actually the hidden code of the universe? Because when you really look closely at how numbers behave, how they interact and sequence themselves, it starts to feel a whole lot less like schoolwork and a lot more like you're on a puzzle-solving detective journey. To figure this out, we're going straight to the source material today, specifically the CSEC Mathematics Module 1 worksheet on number theory and computation. By carefully cracking the code of these specific questions, we're going to uncover the underlying structures of math itself. We're not just going to mechanically solve these problems, we're going to understand the why behind them. So, here's our game plan for today. 1. The anatomy of numbers. 2. Factors, multiples, and primes. 3. Cracking the sequence code. And 4. Real-world applications. Section 1. The anatomy of numbers. The mathematical atoms. Let's look at question 3 on the worksheet. It shows this fascinating relationship where different types of numbers nest inside each other, kind of like those wooden Russian nesting dolls. You start with step 1, the natural numbers, your basic counting numbers, like 1, 2, 3. Then step 2 steps it up to whole numbers, which is just the natural numbers, but we toss a 0 in there. Step 3 expands into integers, which brings negative numbers to the party. Step 4 is rational numbers, covering fractions and decimals that end or repeat. And finally, step 5 wraps up the whole shebang into the real numbers. So, to answer the worksheet's specific question, which subset contains 0 but is not contained in natural numbers? Well, that would be the whole numbers. An understanding that nesting actually perfectly answers question 2 from the worksheet, which asks us to contrast the square root of 2 with the square root of 9. Look at the stark difference here. The square root of 2 is an irrational number. It produces a messy decimal that goes on forever and never repeats. You just can't express it as a clean fraction. But the square root of 9? Well, that's just a rational number wearing a disguise. The square root of 9 is exactly 3, a neat, tidy whole number that you can easily express as 3 over 1. Moving right along to section 2, factors, multiples, and special number types, the chemistry of mathematics. Okay, I want you to look at question 8, specifically the number 91. Just look at it for a second. Is it a prime number, meaning its only factors are 1 in itself? Or is it a composite number, meaning it can be cleanly divided by other things? Your gut instinct probably says, oh, that's definitely prime, right? It doesn't end in an even number, it doesn't end in a 5 or a 0. Well, actually, scratch that. It turns out 91 is totally a composite number. If you divide it by 7, it goes in perfectly, exactly 13 times. So its factors are 1, 7, 13, and 91. It just goes to show that in mathematics, looks can be incredibly deceiving, and you've always got to test your assumptions. Section 3. Cracking the sequence code. Numbers in predictable motion. All right, to tackle question 20 on our worksheet, we first need a quick definition of what we're looking at. We're dealing with triangular numbers here. This is a really cool set of numbers where the quantities can physically be arranged to form perfect equilateral triangles. Check out this visual pattern straight from the source material. Diagram 1 has 1 dot, diagram 2 has 3, diagram 3 has 6, and diagram 4 has 10. Do you see the sequence happening here? To get from 1 to 3, we add 2. From 3 to 6, we add 3. From 6 to 10, we add 4. The gap itself is growing by 1 every single time. So when the worksheet asks us to calculate the number of dots in diagram 7, we just follow the trail. Diagram 5 adds 5, giving us 15. Diagram 6 adds 6, giving us 21. And diagram 7 adds 7, resulting beautifully and naturally in exactly 28 dots. The crucial point here is that this hidden logic exists everywhere if you know how to look for it. Look at this brilliant little pattern from question 13. Row 1, the first odd number, 1, is just 1 squared. Row 2, the sum of the first 2 odd numbers, 1 plus 3, equals 4, which is 2 squared. Row 3, the sum of the first 3 odd numbers is 9, which is 3 squared. you are generating perfect squares just by summing consecutive odd numbers. So, when the worksheet asks you to predict the sum of the first 15 consecutive odd numbers, you absolutely do not need to manually add them all up. The code tells you it's simply going to be 15 squared, 225. Boom. It feels like mathematical magic, but it's entirely logical. Section 4. Real-world application and problem solving. Let's call this the mathematical engineering. Okay, picture this scenario from question 16. You've got 3 lights flashing, and they're all on completely different timers. One flashes every 4 seconds, one every 6 seconds, and one every 10 seconds. Now let's say they all happen to flash together at exactly 12 noon. The big question is, at what exact time will they next flash perfectly together? Without math, you are just staring at chaos. Literally seconds after noon, they're totally out of sync. 4 seconds in, light 1 goes off. 2 seconds later, light 2. 4 seconds after that, light 3. They are operating on entirely different rhythms. We desperately need a mathematical tool to predict when these chaotic rhythms will finally converge again. And that tool? It's the least common multiple, or LCM. If we find the LCM of 4, 6, and 10, we get exactly 60. This is a massive aha moment. That means it takes exactly 60 seconds, or 1 full minute, for all those different multiples to line up perfectly again. So the lights will beautifully sync up at exactly 12:01:00. By understanding multiples, we literally predicted the future behavior of a physical system. Let's tackle one last challenge today, this one from question 18. It throws out this super bold statement. The sum of any 2 prime numbers is always an even number. Now, as a math detective, whenever you hear a sweeping statement with the word always, your alarm bells should be ringing loudly. We need to prove or disprove this. The beautiful thing about math is that to disprove a sweeping rule, you don't need 1,000 examples. You literally just need one single counterexample. And for us, that's the number 2. 2 is a prime number, but uniquely, it is the only even prime number. So if we take 2 and add it to any other prime number, let's say 3, the sum is 5. 5 is an odd number. And just like that, with one tiny counterexample, we've completely shattered that rule. We've cracked the code on a lot today, from classifying numbers to predicting sequences, all straight out of the CSEC math worksheet. But I want to leave you with this final thought. If these basic properties, like factors, multiples, and sequences, can control everything from the timing of flashing lights to the geometric shapes of triangles, what other hidden mathematical patterns are quietly governing your everyday life? Keep your eyes open, because the universal building blocks of math are literally everywhere. Thanks for joining me on this explainer, and I encourage you to keep looking for the patterns.